Welcome to the second week of Automat DEVLOGs. This time we are starting with the assembly project. If you look at Automat right now, you can see that the way we pass control is very linear. Every object has just one output object that it can trigger. We could add some objects that would have several outputs or several inputs that could make decisions. This is one option to actually solve this control problem, to just implement a bunch of objects that will handle all of the possible control primitives. However, we are not going to do that. We are instead going to implement a different solution based on the assembly language. This assembly language, the native assembly for whatever platform Automat is running on. The reason for going with assembly, surprisingly, it may seem, is that it's actually a very conceptually simple thing. If you look at people who are starting programming, try to see what are the most common errors, what do they get wrong. This is typically the syntax of the language. Whenever you want to program in any language, you have to learn the syntax. In assembly, there is some syntax, but very, very little. And actually we can find a way to work around it completely so that we can basically eliminate all of the syntax issues from assembly. Second thing is that it's very easy when you see an instruction to think and to predict what the instruction will do. Then the errors that can happen when you edit assembly, they are also limited. And this is another thing that's very common when somebody starts programming. They get those huge undecipherable errors. In assembly, this is not the case. There are just a couple types of errors. And when an error happens, you can always say, hey, here, this instruction did something illegal, something that it shouldn't do. For example, accessed bad memory. Assembly, because it's very regular, it is actually cheaper to implement than a bunch of high-quality, polished blocks that would help us do control flow. Then there is also the possibilities that it opens, because assembly is executing ridiculously fast, and that it can interact with pretty much any other technology. For example, it can interact with C, and because it can interact with C natively, it can also interact with whatever, Python, C++, JavaScript, anything that you have on your PC. This is a very important technology. We can use assembly to create extensions for Automat, in addition to this control flow. So definitely a very exciting project ahead of us. This is how the initial design looks like. I may open it in a separate app to show you. So we have instruction pointer, which is an actual pointer. Each instruction is a smart instruction block. Maybe. And so instead of editing text, as you would normally do if you were writing assembly, here we can edit it by drag and dropping blocks that represent instructions. They don't map one-to-one to machine instruction. It's more like one-to-many mapping. A single block is able to cover many types of instruction, and it can be parameterized. For example, a multiplication smart instruction will be parameterizable so that you can select it to either work on general purpose registers or the SSE floating point registers, and so on. And then we will have a bunch of cool effects that will make this environment pleasant to work in. So we will have Broadway lights around the environment to indicate whether it's running or whether it's paused. We will use cool scroll animations. This is still to be implemented, but we have some nice ideas. And then we have many more ideas. For example, how to represent registers in a fun, interactive way. We already have a prototype. First, let me talk a little bit about it. So we are using LLVM as an assembler And this means that we can target many architectures. Of course, there is x86, this is the one architecture that we are starting on. But in addition to that, we also have anything that LLVM supports. Assembly executes its native speed because we run it in a separate thread. But even though it's executing at native speed, we have two very important features. First is that we can still access the registers. So it's still executing at native speed, but whenever we have to render frame to display it on screen, we can ask the operating system to pause this thread, get a dump of registers, show it to the user, and continue. This is what will allow us to render all of those fancy effects. And the second big feature is that we can catch pretty much all types of errors that assembly programmer would typically encounter. So whenever there is invalid memory access, floating point exception, illegal instruction, in all of those situations, we can basically get a signal callback. We can pause the execution, and in our environment, we can tell the user, hey, we are here, and an issue happened. What do you want to do about it? Okay, and now time for the demo. Because it's a prototype, you kind of need to understand what you're looking at. So what happens here is that we are emitting a bunch of machine code, and then we are inspecting state of all the registers. There is some machine code that is executing in a separate thread with this thread PID, and then every second we are pausing this thread to get a dump of all registers, and then we display it on screen. After 10 seconds we are stopping the execution. And that would be it. Thank you everybody for watching, and see you next week.